and he will talk about stochastic nonlinear fractional Schrödinger equations. So please.
So again, welcome from Cambridge. Sorry for these technical problems, but now I think everybody else will be able to do the same. So I will speak about some results which were, from my point of view, the main focus of the results which we obtained. Yeah. So actually, I need to go to the previous page. How to go to the previous page? Sorry. Now, this worked. Okay. Okay. I don't know. So these results have been obtained together with Fabian Hornung and Lutz Weis from Karlsruhe, and I will also speak about some results with Benedetta Ferrario and Margherita Zanella from Pavia and Milano. And as I say, I decided to speak about this because when I came here, I realized that I don't really understand very much, and it turned out that we had such results in the papers about these fractional Schrödinger equations. So I want to extract the results which were quite more general to the particular case of fractional equation and describe what those results are. So I start with the equations. The equation is the usual one. It's stochastic Schrödinger equation. We write them in this way, where we have I on the right-hand side. And so we have minus IA, minus I, A, U. So A is a self-adjoint non-negative operator on a complex Hilbert space H, L2 with values in a set of complex numbers. F is certain nonlinearity, so the F is just a function from H to H, but with some domain in H. And W, I have to move, because this is, do you see this bar, or you don't see any bar on your screen? Okay, you don't see it. And W is a symmetrical Wiener process on now it's stopped working.
We don't see the bar.
Okay, it's good that you don't see bar, but my shifting the pages is again stopped. I have to move pages by hand. Okay, it's complicated this way. So we have a Hilbert space L2. We have a sequence of identical IID Brownian motions. The stochastic term, which I wrote minus IB of U Stratonovich dW. No, I don't know what is happening. Sorry. Okay, it's a lot of problems. I cannot move the pages again. Oh, now I can. So what we are doing here, I will speak later. We consider equation in Stratonovich form, so which is it is a formal expression which contains of the Ito form plus some correction, and I will speak about this correction slightly later. So what in the first part of the equation, we are looking for this situation where everything is sort of real. So in particular, the L2 norm of the solution will remain constant. This is not the case of later parts when I will speak about invariant measures. So the motivation apparently for nonlinear Schrödinger equations is that it's not quantum physics. Okay, at least one of the motivation is something which is called photonics, and people consider a very long cable with some cross section, like so. In this cross section here is from a two-dimensional disk, and the t, which we usually denote think of time, is just the length of this cable. So in some applied papers, they use actually parameter z. So as I said, this so this is the time, this is the domain. So the domain can be a subset of RD, which can be bounded sufficiently smooth domain, or it could be a compact Riemannian manifold, or it could be a smooth domain in a compact Riemannian manifold. So many situations, but mostly I will speak about, say, the case 1, 2, and 1, 3, about where the domain is compact. And the whole model can be set up in such situation that one can also consider fractal sets, etc. So what I will speak here is a very particular case where the operator A is the fractional Laplacian. And that was already mentioned, I think, in Eulalia's talk, what exactly is this operator. So my operator A is the fractional power in the sense of functional calculus of operator with prescribed boundary conditions, which is self-adjoint. If the domain is full Riemannian manifold, then the operator A0 is simply Laplace-Beltrami operator, and then A is again fractional power of this Laplace-Beltrami operator. And we do not consider such operators here as very popular recently in this particular linear theory, where you define the operator on some open domain in RD, and the boundary conditions are actually prescribed on the whole complement of this operator. So this is maybe something which would be interesting to do. So about the nonlinearity, so I consider nonlinearity mainly of the form f alpha plus or f alpha minus, or a linear combination, but I will speak about these two cases separately. And one of these cases is when we have plus here, and then it's called the focusing case, and when you have minus, it's called focusing case. So the focusing case is somehow simpler, because again, I will write later, when you write down the corresponding energy for the deterministic equation. And for deterministic equation, if the solution is smooth enough, this energy is preserved. So in the defocusing case, the energy is a sum of the kinetic energy plus potential energy, and this potential energy becomes positive, which in the estimate makes it much easier. In the focusing case, this is opposite. So you have a positive kinetic energy and negative potential energy. And this is why you need constraints on the parameter alpha. So the question is, what I want to present is, so when we fix beta, dimension, and alpha, for which alpha respect to beta, the problem is well posed. And I will speak firstly about the Martingale solution, where I will not speak about uniqueness of problems. So I will just present how this alpha depends on beta in order to problem be well posed. So now I come back to this stochastic part. So if I denote the nonlinearity by g of u minus I bu, then g of u straton of gw, and that is the definition, is the Ito integral plus the correction term. And to make sense of this correction term, you need to consider some Banach space E, such that the embedding from, remember, K is the Hilbert space on which we have a cylindrical Wiener process, and the embedding is gamma radonifying, which actually means that the cylindrical Gaussian measures on this space are true Gaussian measures on the space E. And so that's more of, or another way, if I take the image of the cylindrical Wiener process, then this image becomes a true E-valued Wiener process. And EK is the orthonormal basis of the space K. And so in this context, we assume that the function G is from H to these linear operators from E to H. And we look at the Fresher derivative, so the object which we write in this trace is the bilinear form from E cross E to H. And then because of the embedding being gamma radonifying, the trace of this bilinear form makes sense. So if I have bilinear form, I take trace defined in this way. And in special case where we have some sort of linear expressions, this trace can be expressed in this correction term minus bk squared u. So this is well known, and now going to operator A. So remember, A is a self-adjoint operator on the Hilbert space H, like fractional Laplacian. We introduce the space which is domain of the square root, and this domain is endowed with the graph norm, which is also Hilbert space. So it's u squared plus a1 half u squared. So we have to add this one because A is only non-negative, like Laplace-Beltrami operator or operator with Neumann boundary conditions. And then we have some kind of a very strange assumption, which actually in our situation is not so strange, because it only actually makes assumption on how regular the domain is. But in this abstract setting, which we have considered, this is because what we just assume is there exists an operator S, which commutes with operator A, with domain for sufficiently large K is embedded in the space. Here should be EA, not EK. And this operator A satisfies some so-called generalized Gaussian bounds. I will not speak about what they are, but I will, at the end of my talk, explain how this operator S is used in the proof of existence. And now about nonlinearity. So we have defined the space EA, which is the domain of the fractionals domain. And I want to remind you is that our Hilbert space is not an abstract Hilbert space. The Hilbert space is, where is it? That's an advantage to use a blackboard. Okay, it's L2 space. Yeah, so the Hilbert space is L2 space. So on some domain, so we can speak about what is the LP space. So we assume, we consider the P maximum, which is the maximum P, such that the embedding from EA to LP is continuous. And as a nonlinearity alpha, we take alpha such that which is less than or equal to P maximum minus alpha. But also we assume that EA with embedding into L alpha plus 1 is actually compact. And so even in the non-fractional case, in dimension 3, this EA is just a Sobolev space H1, 2. And everybody knows that H1, 2 in three-dimensional case is embedded continuously into L6 space, but this embedding is not compact. And what I wrote here before is that this condition can be replaced by the word continuous, so according to Fabian Hornung work, but I got an email from Fabian today, which I asked him, and he claims that it is not true. So he still needs this alpha smaller. So more or less what we say is that even in dimension the non-fractional case, we have to assume sort of assumption like this one. So which means that our existence results later on is only true for alpha less than 6, no, less than 5, but not equal 5. And so it's a small open problem whether the result is true or not. And I want to explain what does this mean in particular case. So if I consider operator A, which is like minus Laplacian to power beta, so it could be Laplace-Beltrami operator, it could be Neumann Diffie boundary conditions, then roughly speaking, the domain of A power 1/2 is again, roughly speaking, the Sobolev space H beta. And then you can check, and I have checked the calculations, that this P maximum is equal to this number. So if beta is less than equal to D over 2, the P maximum is infinity, but if beta is bigger, then this P maximum is equal to this one. So then we have the condition that alpha plus 1 has to be less than equal to P maximum, plus the compactness condition, which I mentioned, is equivalent that alpha has to be satisfied in the set. So in other words, this means that the assumptions on F, which I mentioned, no, maybe this one, not the assumption F. This means that this assumption that the operator EA is compactly embedded into L alpha plus 1 and alpha is less than equal to P maximum minus 1 is equivalent to this condition. And actually, I will the result I will speak about is just showing that this is a condition which we need to prove existence of actually global weak solutions, global solutions, but not uniqueness. So what is the main result here? So the theorem 1 is exactly the same. There exists a global weak martingale. I added weak word here because sometimes people have different definitions, and I will not repeat the definition because it is some standard. So when this global weak martingale exists, we have these two cases. So we consider the focusing case where f of u is the positive number, this expression was with positive sign, and then exactly the condition which I mentioned on the other slide is satisfied. So if alpha is up to this number, then there exists a global weak martingale solution. However, when we consider the focusing case, then the condition for alpha is much smaller. So we need to assume that alpha is less than 4 beta over d. So d is the dimension of the space. The same as d is here. And why? Okay, this is again a result from kind of a general assumption, but the reason is that the energy is, in this case, is not fully positive. So when you try to find out a priori estimates, you have some a term which is negative, and this negative term has to be absorbed in something which is positive. In this case, there is no negative term, and there is positive term which can only help to have a priori estimates. So when I say exists, so we consider initial data in this space H beta, which is domain of A to power 1/2, and this there exists a solution which satisfies this a priori estimate. So for every t, the function u is bounded with values in the energy space, and moreover, this u is weakly continuous, weakly evaluate continuous process. So it is not only bounded but also weakly continuous. And so I want to speak a little bit more details about the assumptions. So When we consider general F, in the defocusing case, we assume that this, okay, so sorry, but there is something, some order is wrong, because I think I started the assumption, but okay, I need to come back to that part because there is a wrong order. So about the nonlinearity. So what our nonlinearity is this polynomial sort of nonlinearity, and so it can be more general. It can just be not. But what we assume that the f is a function from L alpha plus 1 into L alpha plus 1 over alpha. And this nonlinearity is bounded by some expression constant, the u to power alpha. We also assume that f of 0 is 0. And we make this assumption here about f, which implies that, as I said, the f is somehow a real function. So this one of the assumptions would imply that the L2 norm is preserved. We also assume that the function f is of C1 class, and the Fresher derivative is bounded by some constant, but with multiplied by the norm of u to power alpha minus 1. And then we assume that there exists a function which is called antiderivative, but it's really a real antiderivative, which therefore satisfies and it satisfies this condition. So if I go back to the assumptions about this, because I was talking about this real antiderivative, so is in the defocusing case, this real antiderivative is some kind of a coercive, so it satisfies such inequality. In the focusing case, we assume that minus f satisfies such inequality. And in the focusing case, so I forget about the bottom of this page, we actually assume what is easier here. We assume that the L alpha plus 1 norm can be interpolated between the L2 space, which is H, and the energy space, which in our case is just H beta. So, and these are the conditions which we require. So why we need this condition? Because I say the negative term in the energy estimate we want to absorb into positive terms, and that is what we actually need. I mentioned about the energy. So the energy plays a crucial role, which is this 1/2 of L2, so the kinetic energy. Okay, I don't know, maybe it's kinetic. I call it kinetic, but it is L2 norm of the square root of A plus this antiderivative. If we consider the function as in the defocusing case, which is this polynomial, the f hat is just constant multiplies the integral of u to power alpha plus 1. Yeah, so L alpha plus 1 norm of u to power alpha plus 1. So in the defocusing case, this energy is non-negative. Why in the there's a mistake. So that is the defocusing case, but this is the focusing case. So it is my mistake. This additional term is negative, so the energy changes sign, and that is a reason for difficulty. I thought about B, so I can say a little bit more about operator B. Just one example. So the B can be linear operator from H to gamma Radon-Effine operators, which in this case are Hilbert-Schmidt operators. And if I denote Bk of U as B of U acting on the eigenvectors, we assume that the Bk is self-adjoint. And in the more general case, we assume that a real part of IU, G of U on every Ek is 0, which is an assumption similar to the assumption about F, and again, which is responsible for the L2 norm to be preserved. And But then we have some technical assumption about this diffusion coefficient. Because we consider equation in the Stratonovic sense, we have to have this addition space E, which I introduced before, and we assume the operator G maps the Hilbert space H into linear operator. It maps this space, the energy space, into linear operator from E to EA, and it also maps this Banach space into the linear operator from this addition space E to the space L alpha plus 1. So if you remember that the space E is chosen in such a way that the embedding from K to E is gamma radonifying, in the first two cases, it implies so that this space is embedded into gamma radonifying, so Hilbert-Schmidt, gamma radonifying, so Hilbert-Schmidt. So it would mean that our operator G from H maps H into Hilbert-Schmidt operators, Hilbert-Schmidt, but in the last case, it maps this Banach space L alpha plus 1, so Lebesgue space into gamma radonifying operators from K into L alpha plus 1. However, these are weakest statement. We need to assume this stronger statement in order to make sense of the correction term. So I already spoke about this part because this slide should be moved earlier. And I want to speak, okay, so my talk becomes very short actually, about uniqueness. So actually, we do not know much about uniqueness in the fractional case. So we know a lot about uniqueness when beta is 1, and beta is 1, which means it is not the fractional case. And so what do we know? So at least, by the way, what I'm presenting is based on my work. There is a lot of works by Michael Reckner and Zhang, who have different approach to nonlinear Schrödinger equations, and also earlier papers by Arnaud Debouche and Anne de Beauward, but they mostly considered full space. So when d is equal to and no fractional operator, but just beta 1, then we have uniqueness for alpha, for any alpha. And that was actually proven by myself and Annie Mier a couple of years ago. However, when d is equals 3, we have a recent paper with Fabian, Hornung, and Lutz, Weis, and actually a very complicated paper where we only can consider to prove uniqueness alpha between 1 and 3. And our uniqueness result is independent of whether the problem is focusing and defocusing. So, and here is something interesting. Namely, we prove uniqueness for a range of exponents from 1 to 7 of 2, however, from 1 to 3. However, when we speak about existence of weak solutions, the conditions are much stronger. So alpha from 1 to 7 over 3. So there is kind of a small open problem. Maybe already the answer is known in some unknown result to me. But it is some kind of strange that we have uniqueness for larger class and existence for smaller class of problems. So I don't know what's going on. So I wanted to mention here that the uniqueness part needs different tools. So in the proof of existence, as I will come back in a second, we don't use the Strickert estimate. So the Strickert estimates go back to Strickert, and there have been a lot of work on this topic. I just mentioned 2 papers which we use. So there is a Burgzer and Svetkov from 2004, who proved Strickert estimates for compact Riemannian manifold, and Blair Smith Sog, who proved Strikat estimates for bounded domains in compact Riemannian manifolds. So you could consider Riemannian manifolds with boundary and the Neumann or Dirichlet boundary conditions. And concerning stochastic Strikat estimates, there are many different ways of doing it. In my paper with Animier from 2014, we provided as kind of a axiomatic approach how to derive stochastic Strikat estimates using some properties of UMD Banach spaces, Burkholder inequality and Kahane inequality. So whenever we have a deterministic Strikat estimate, we can derive stochastic Strikat estimate by the same method. But as I say, this is all for case beta equal 1. And again, a mistake with beta equal 1. So when I wrote beta equal 2, I meant minus Laplacian. So it should be beta 1. So I wanted to say about invariant measures. So in the previous work, we already make assumptions such that L2 norm is preserved. But this assumption turns out to be not necessary. You can remove it, replacing it by some natural assumptions. And using some unnatural assumptions with Benedetta and Margherita, we proved that there exists invariant measure. And we prove it again for non-fractional case. So the question is what happens for fractional and for any polynomial. And concerning fractional cases, what we have in progress is that we can introduce such a problem where operator A epsilon is small perturbation of the fractional Laplacian by Laplacian. And you can also see this operator A epsilon as a perturbation of Laplacian by fractional Laplacian. And using this one, you can prove that Strikat estimates holds for such operators because they hold for minus Laplacian. And because this is more or less as in the previous work with Margherita and Benedetta, you can prove that there exists invariant measure mu epsilon for the Markov semigroup generated by this equation. And as I said, this is a work in progress. Once you have invariant measures for such equation, you can construct Martingale solution to the original problem. So original problem is epsilon 0, for which we don't have uniqueness, at least at this moment, and therefore we cannot speak about invariant measure. But despite lack of uniqueness, we can speak about stationary solutions, and then we believe that using the same technique as a paper with Benedetta, we can prove there exists stationary solution. So concerning these topics about invariant measures, most the questions are open for fractional Laplacians, at least in my understanding. Stop working again. I don't know. Okay, so now I want to speak about the proof of existence and point out what is interesting. So the H is our complex Hilbert space. We consider the first eigenvectors and the Hilbert space generated by the first eigenvectors of the operator A. And we consider the orthogonal projection Pn, so it's not written orthogonal projection. So in that situation, the natural way to approximate our problem would be to write down this equation 11. So Pn is commutes with A, so we don't write Pn here. We have Pn here and Pn over there as well. So now this is a classical Galerkin approximation. However, there is a problem, namely these Pn's are uniformly bounded in L2 space, but they are not, because PNs are not uniform bounded in these Lebesgue spaces. So, and that is what we need. And now comes a moment which is new to the previous result, but this is that we can introduce other projections which are not orthogonal, and that is where we use this operator S. So using little Pauli theory, one can construct a sequence of operators Sn with the following property, that Sn is operated from H to Hn, is linear bounded. It strongly approximates identity in the energy space. So Sn u converges to u in the energy space. These operators are contractions in both H and in the energy space, and they're uniformly bounded in the Lebesgue space L alpha plus 1. So this is something new. And then the problem 11, which I wrote, we can modify, and we modify it only in the stochastic part. So where everywhere we have Pn, so if there was no stochasticity, then there would be no need to the operator Sn. But because the problem was with the stochasticity, when we introduce Sn, it allows us to obtain the necessary bounds in the space in the Lebesgue space L alpha plus 1. So one can prove that this new problem has a unique, strong global solution, Hn valued. L2 norm is somehow not preserved, but it is not exploding, and the following estimates are satisfied. So remember that this energy E contains the L alpha plus 1 norm of the solution, and that is why we needed this Sn. So we prove that this sequence Sn satisfies such uniform estimates. It satisfies the Aldous condition, which I will not mention, and therefore, if we introduce this space for fixed t, the spaces of weakly continuous functions with values in the energy space, which are continuous in the very big space, because the very big space is a dual of the space EA, and this this Lebesgue space, L alpha plus 1 respect to time, L alpha plus 1 respect to space variable. Then by Skorood-Jakubowski theorem, you can find a probability space, a subsequence, and we can find new random variables on this new probability space with values in our topological space, such that the low of the new random variable is equal to the low of the random variable from this subsequence, and the new random variables are convergent to a limit random variables on the space Zt. And this U tilde is here the same as this V, because I changed it, but didn't change here. So this limit random variable satisfies the estimates, the same estimate as the approximate. And then by a lot of technical work, one can prove that one can find a Wiener process, cylindrical Wiener process filtration, so that the whole system is a Martingale solution. So there is a lot of technical work, which is sometimes similar to other work in, for instance, Navier-Stokes equation. The whole, it is possible to do it because we can construct this sequence Sn satisfying this uniform bound. And I think that is the end. So the end is that also the L2 norm is preserved. In the case of the work with Benedetta and Margherita, we look for invariant measures. The assumptions on the nonlinear are slightly different, and this condition no longer is satisfied. But in this case with Lutz and Fabian, we prove solutions satisfy this condition. So thank you very much for your attention. And if yes. Now,
thank you.
Okay, you are unmuted.
Yeah, so time for questions. You can unmute yourself and and ask questions. Michael.
Yeah, thank you very much, Zdzislaw, for this very nice talk. I have one question. I mean, the restrictions on the exponents that you had, is this due to the noise? So if you look just at the deterministic equation, will you have the same restrictions?
I mean, I don't know. I mean, probably yes. It is not because of the noise, but if you look at the condition on restriction, is just because the interplay between the linear part, the domain of A, and the nonlinear part, which is the LR plus one space. So more or less, and it is. So if you take noise 0, you will get the same result. Probably in the deterministic setting is not interesting. Although I haven't seen that result, because people usually look for strong solutions in the deterministic case. Although, for instance, there is some small argument in the paper of Burg, Gerard, and Svetkov, which I mentioned in 2004, where they use some compactness to prove existence of solution in the critical case. So there is, but it is exactly, so the answer is yes to your question. Yes, so we have the restrictions on alpha and beta are because of the deterministic part. So,
okay, because I'm asking, because there in the Boas and the Bush work, they had some restriction on the dimension because they need some strict stochastic estimates that were due to their noise. And when we did our little bit simpler noise, but that we could transform, we could get rid of these restrictions. But you are saying in your situation there is no such.
No, I think I don't. So I think that. I cannot really prove what I say now, but I think that our stochastic Strigat estimate are stronger than Ans and Arnaud, but I really didn't fully check such a statement. So I think we don't, so our assumption on noise are somehow weaker, but you have to remember also that Arnaud and Anna were working the full space, where it's actually a little bit more difficult, but also they work with the strong solutions. So they used Strigat estimates. They used Strigat estimate to construct a strong, unique solution. The same what I was doing with Animier, and probably you also have been working with strong solutions, I think. Yeah. So,
but is there a paper in the deterministic case exactly in this situation?
That I mentioned, I don't know. I can show you where, and a small paragraph in the Burg-Gerard paper, where they use some compactness result, but they do it on two lines, not even 2 pages, where something is mentioned about compactness method. And maybe for people, such a result would be trivial. So what I wanted to somehow to say this is that it seemed to be kind of a very straightforward, apart from this difference, which I mentioned about this operator F and this approximations. And yes, and again, the beauty of, okay, don't say beauty, yeah, but the nice part of the feature of the paper with Lutz and Fabian is that we have very general setup. Settings which also can include fractional domains, fractals, etc. So what I wanted to point out, what are the results? So in a sense, sometimes when you speak about fractional Schrödinger equation, okay, you can say, okay, at least some results are known. So when we work on other problems, let us try to find out results which are not unknown. And so I wanted to point out which results are known in this situation. And I don't know deterministic result which would contain this one. Maybe for those people it's trivial.
Thank you.
It seems there are no more questions.
No. So, so thank you again for this interesting talk. And we meet back at 2 p.m. for our next seminar.
Okay.
Bye-bye.
Bye-bye, everybody.
Bye. Thank you. Goodbye.
Bye.
Bye.